Hi everyone, my name is Donciu-Julin. I'm an AI software engineer, and as part as a recent job interview, interview process, I was asked to present a paper on Mistral 7B, and this gave me the opportunity to go in depth to read the paper, go in depth into the architecture of Mistral 7B, the key choices that Mistral AI has done in its implementation, and especially understand why it was a revolution when it came out last year. So I thought it would be interesting to share this knowledge with you and maybe discuss it further and see, learn a little bit more about Mistral 7B. This is the paper we're going to discuss. It's called Mistral 7B from the company Mistral AI, and it has been released last year in October 2023. You can find it on Arxiv, and we're going to see what is hiding behind this amazing word art title. So in my presentation, I'm going to lead you through a brief model overview. We're going to check especially the context it was released in last year and the promises laid out on the paper. We're going to dive into architecture. This is the interesting part. We're going to try to understand the key design choices that Mistral AI has done and what makes it actually so performant. Obviously, we're going to look at the benchmarks and see how it compares with the other open source model at the time. We're going to discuss fine-tuning and see how well it can generalize and tackle real-world projects, real-world use case. We will have a look at guardrails and safety measures that can be implemented to make sure that Mistral is generating responsible content. And finally, we'll have a look at key use cases where Mistral particularly shine and conclude with some key insight and, well, still open discussion points. I will try to keep the presentation under 30 minutes, but I tend to speak too much when I'm interested, so let's dive in. Okay, before presenting you Mistral 7B, I want to put you in context, and I want to dive back in time with you. Let's take a trip back in time and go to April 2023. This is the beginning of last year. It seems like right yesterday, but a lot of things happened in the past 2 years in the AI industry. And in April 2023, you have three guys, Arthur Mensch, Guillaume Lampel, and Timothy Lacroix, that are AI engineers coming from different companies like DeepMind, Google DeepMind, and Meta. And they decide to team up, and they found a startup called Mistral AI. And in about a month, they raised $113 million funding. And by the end of the year, this funding amount raises by 415 million. Obviously, when you're a strong startup, when you're a young startup and you raise so much money in so little time, people start asking questions, and everyone was wondering why, what are they doing, who are they, and what are they doing? And the answer didn't take long to come, because they released their model in October. But to put you again into context, right before the release of Mistral 7B, the AI market is mostly dominated by proprietary giants like OpenAI GPT-4 and Anthropic Claude. You do have some open source. Models like Llama from Meta, Llama 2, Llama 1, Llama 2, that are kind of like the only open source alternative at this time. And you have some niche open source model like Falcon, MPT, that are good, but in their own domain, like they are good at addressing specific use case. And at this time, the paradigm is that bigger model gives you better performance. So you need a model as big as possible to get the best performance possible. And I think this is where Mistral struck pretty hard by showing that this is actually not always the case. That's it. We're in October 2023 and Mistral 7B is released. Quickly speaking, Mistral 7B is a large language model. It has 7 billion parameters, so that seems a lot, but compared to the 175 billion parameters from GPT-3 or GPT-4, which is 10 times bigger, this is actually a very small model. And what strikes immediately on the paper is that it outperforms the Llama models, so which are again the direct open source comparison at the time. It outperforms the Llama model on most of the benchmarks. So it is a model that generalizes incredibly well. And what's even more surprising is that it's approaching the coding performance of Code Llama. So Code Llama is a Llama model that has been fine-tuned to produce code. And out of the box, Mistral 7b can approach its coding performance without doing any compromises on the other benchmark like text generation. So this is very impressive. It is showing superior performance and efficiency thanks to different strategies we're going to discuss later, like the sliding windows attention and the group query attention. It is released as a native and as an instruct version, meaning that Mistral AI is not simply showing some result of some research project. It's not just mentioning, hey, we researched this thing, we made this LLM, it's interesting, let's share results. No, they are releasing a model that they are already aiming at using on real use case scenario. And to even enforce this idea, they release a wide range of scripts to speed up inference like VLLM or cloud deployment like SkyPilot. So this model is aimed at being used immediately on real use case scenario. And cherry on the top of the cake, the model is released on Hugging Face, fully open source under the Apache 2.0 license. So this is a strategic point. It means that anyone can take Mistral 7b, change its code, commercialize it, make money, gain model, earn money with it, and doesn't have to share any of this updated code of this internal code. So this is an incredible opportunity for anyone working on the AI industry, and Mistral immediately placed itself as a direct concurrent of the other open source models like Llama. Okay, let's dive into the flesh, the hard part, the model architecture. Before showing you the architecture of Mistral, I want to do a quick recap on transformers. If you're not familiar with the architecture, let's do another bigger step back in time to June 2017, where a paper called Attention is All You Need has been released. That's the one that you can consult also on Arxiv. This is probably the paper that has this is probably one of the most famous paper in the AI industry of the past 15, 20 years. And if you have only one to read, I would encourage you to read this one. Just to put you back again into context, we are in 2017 and a team of Google engineers are trying to improve Google Translate. And to avoid to improve the quality of the translation and avoid a word-by-word translation, they come up with a very complex architecture that they call the transformers architecture that allows, when translating a word, it allows the system to attend the words around it. So to take the context of the word into consideration to translate it. And again, this is aimed at improving translation. And when they release this architecture, so this is the architecture that you can see here. It's a very famous schematic you can see all around. They are using attention layers, so the orange blocks mask multi-head attention and multi-head attention blocks. And so a combination of attention block and feed-forward blocks, so multi-layer perceptron blocks. And the combination of the two allow much more precise translation by using the context around the words. And it's contrary to, it is like a next step, an improvement of what was used before, like the RNNs or the LSTM cells. And on top of it is fully working using embedding, so you can input text directly and output logits, and this text is going to be transformed into vector embeddings and integrate encode the position of the tokens, and then all of your tokens are going to run into these blocks and that are going to output the most probable token. I don't want to go too much into the transformer architecture, but I just want to say that when this architecture came out in this paper in 2017, the Google engineers, I think, had no idea of the impacts of this paper on the AI industry. They had no idea that by creating this architecture, they had shaped the future of AI for probably the next 20, 30 years, because all of our LLMs today are built, most of the LLMs today are built on improved version and improved and fine version of the transformer architecture. And they had no idea that this architecture that they made to improve translation could actually allow large language model not only to generate better output, but also to some extent to reason and to think. It is still a wide topic if LLMs are really thinking or just simply outputting stuff they have learned. But they had no idea of the impact of this architecture. This brings us to Mistral. So as you can see, Mistral is it's a very similar architecture. It's using only one decoding block from the initial architecture. But inside the block, you can find the exact same blocks, which are the multi-head self-attention heads and the feed-forward MLT, multi-layer perceptron networks layers. And it's using 32 of these blocks, so 32 attention layers, 32 attention blocks in a row. And the rest is more or less the same. You have the same text input, embeddings, encoding, positional encoding, and up to the output probabilities. The paper is giving us some values here that I transcribe to understand them better. You have an input context window of 8K tokens. I think like GPT-4. Yeah, context windows of 8K. Yeah, GPT-4 had different context windows. You have a vocabulary size of 32K tokens, so that's the amount of different tokens that can be embedded, that can be changed into embeddings, so 32,000. Vocabulary size, you have embeddings of size 4K, so your vector embeddings have a size of 4,000 dimensions to encode all of the meaning of the tokens. Your attention heads, the attention heads, you have 32 attention heads for a total of 128 dimension, and 32 attention blocks. So all these gray blocks you have 32 of them in a row to allow, as we will see, to attend to a wider scope, wider window. We'll discuss it in the next slide. And finally, as the transformer architecture initially was, you can directly work with text input and text output. Okay, now let's have a look at the key optimization that Mistral AI has implemented and that makes Mistral 7 be so efficient. The first one is addressing one of the main issue of the initial transformer architecture. If you look on the left, you have the vanilla attention, which is the one used in a model like GPT-3 and that are coming from the initial architecture, transformer architecture, is that your attention, each token can attend to the full size of your context window. So if you work, for example, with a context window of 8K tokens, 8,000 tokens, your last token, you want to generate the next token, and your last token actually can soak up information from the 8,000 tokens behind it. So it can get the knowledge, it can be influenced by the knowledge from all of the 8K tokens around it. And in most of the use case, this is overkill. Like you don't need this size, this context size, this amount of context. And this is highly unproductive. Why? Because all of these context possibilities requires calculation. So inside your attention head, you have mostly, the calculation are mostly matrix multiplication and inside between embeddings. And so your last token can incorporate the knowledge and the attention can attend to all of the other. You need, of course, a lot of calculation, and not only calculation, but you also need a lot of of memory size to store the intermediate step of all those calculations. And this is a problem because if you increase the size of your context window, then you exponentially increase the calculation, and we have a complexity in the case of the vanilla attention of O(n) square, n being the number of tokens that you have that can be attended. So if you increase those kind of model, this kind of vanilla attention doesn't scale well. What Mistral did is that they implemented a mechanic called the sliding windows attention. So this is coming from a paper called the Longformers. I think I have it here from April 2020. Yeah, I think that's the one. Okay, I didn't have time to read it, just had a look at some of the explanation. But you can see that it's the same. Instead of using the full n square attention, it's actually using a sliding windows attention mechanism. And this means that your token cannot attend to the full context window of tokens, but only to a given window size of, in the case of Mistral 7b, 4K tokens, which is half of the context size. So this is drastically reducing the amount of calculation and drastically reducing the memory footprint, the memory you need to store those intermediate calculation results. As a result, the improved complexity, instead of being O(n) square in the case of the vanilla attention, is of O(n)W. So n amount of tokens, W the size of your window. And this is growing then linearly and not exponentially like in the vanilla attention. So it means that Mistral 7b scales well if you work with larger context windows. That makes it of Mistral an very efficient at handling a long context document. Let's pause a second and wonder if this is not actually impacting the performance of Mistral, because we are like putting some blindfold and preventing Mistral to see actually as much as it could, and we are preventing tokens to see the full scope of the other tokens, the full context window. But this is also where the sliding, it's not just a window attention, it's a sliding window attention. This is where Mistral is leveraging the fact that the transformer architecture is working on layers. So as we have seen earlier here, we have 32 attention layers stacked on top of each other, and it is using the stacked approach, the stacked architecture of the transformer as an advantage by sliding this window of attention from one layer to the other. So here I also improved a little bit this schematic from the paper that was a little bit hard to read. I added the square here, so you can see actually that when moving from one layer to the other, the top one being the last layer, this very last token has soaked up information on the last layer from this window attention. Here, in the example, we are reducing the window to 4 tokens for the example. And those 4 tokens, actually the first one of these 4 tokens has soaked up knowledge from a sliding windows of 4 tokens behind it, meaning that every time we go from one layer to the other, we slide this attention window, and the tokens inside the windows are attending indirectly to the token from the window next to it and from the window next to it 32 times inside these attention blocks. And this is why in the end this very last token incorporates hold the knowledge, in its embeddings, it holds some of the knowledge from tokens that are far away and far outside of its attention window. So this is how, by using these stack layers, the tokens can still attend to a window which is much larger than the window size limitation. And I think it says in the paper that it can, in theory, attend to 131,000 token. It's kind of like, by using this mechanism, it's kind of like you have access to a window. You can attend tokens inside a window of 131,000 tokens, which is pretty big. This makes of Mistral a model that is very efficient on at long context handling. It's very efficient on large document. And the inference time, because we are reducing all of those calculations, makes it that the inference is much faster, and the inference speed is multiplied by 2. It is 2 times faster on large document to convey and generate the next tokens. That makes, as I said, Mistral 7b, that makes of Mistral 7b a very scalable model and very hardware friendly due to the reduced amount of calculation. I hope this is all clear. This was a bit tricky for me to understand all of this. We're going to see it in the next strategies. The next strategy is directly linked to the sliding windows attention. This is a rolling buffer cache. As we said, all of the internal calculation and temporary result needs to be saved inside somewhere, and they are saved inside a buffer cache. And because we are reducing the size of this, because we are reducing the calculation, the amount of calculation, we can also reduce the size of the cache. And the cache size is set to exactly the size of the window. This is obviously a precise choice, an implementation choice. This is a way that every time you produce a token, if you take the last line, for example, the cat sat on the mat, when we produce the next token after on, the cat sat on, so you're going to produce because of the fact that we don't need the beginning of the cache anymore. We have used it already to produce. We have used the cat to produce sat. We have used cat sat to produce on. So we don't need the beginning of the cache. We can use, as we have been using a sliding window attention, we can use a rolling buffer cache, meaning that the next token is going to override the first one using a modulo system. So the is going to come in the first position, and when we produce the word mat, it's going to get on the second position and override the word cat. So this rolling buffer cache makes sure that the memory is used as best as possible. It allows to reduce the size of the memory, reduce the memory footprint, and while still reusing overlapping result, because the tokens are still saved in cache temporarily for a certain amount of time until this modulo system overrides. We can still use overlapping result. As a result, this is an optimization of the memory, but about 8K. You have an optimization, and you can reduce the memory size by 8 times for 32 tokens. So this rolling buffer cache is directly linked, as I said, to the sliding window attention and allow a very efficient use of the cache to store internal and temporary results. Last but not least, you have two additional strategies amongst many other, but I'm presenting you the main ones that are presented in the paper, explained in the paper. You have a chunking mechanism and a pre-feeding mechanism. This is a way to chunk long sequences. So when you have long sequences and you know already the prompt that you are inputting into the LLM, you can already chunk it into chunks. You can split it into chunks, and obviously the size of the chunk is matching the size of the cache and the size of the sliding window. It's a little bit complicated here in the schematic, but if you look, you have 3 chunks displayed. The last one is actually the chunk that is being processed. It's called the current chunk. We are producing actually still on the same example as above. The cat sat on the mat and saw the dog go to. We are producing actually the tokens that come after the dog go to. And to produce the next tokens, we are going to access the cache, which is the middle chunk. The cache is what has been saved earlier, the token saved in cache, and our current token are going to attend the token in the cache to produce the next one. And because of the sliding windows attention, they cannot attend past tokens that are outside of the cache. But again, because of this stacked layer architecture, they still have access inside the cache. You still have some knowledge retrieved, soaked, influenced by the past tokens. So the past tokens cannot be attended, but somehow are saved, are there inside the embedding saved in the cache. This is a bit tricky to understand, but this knowledge is traveling chunk by chunk, and your current token is actually theoretically attending all of the previous tokens, as we said, to produce the next one. And this chunking system, being the same size of the rolling buffer cache, and being the same size of the window size, makes it highly efficient at processing, saving internal temporary results, and generating the next tokens. Finally, the group query attention, I think, because I put Arxiv here, that is also being implemented from another paper. That's the one. It's another paper from December 2023. Okay, so it's actually was released, or maybe it's the date it was saved on Arxiv. But it's about yeah, I guess a paper that came probably at more or less at the same time. It's that it's a bit different. It's grouping the query attention. So let's go back to the transformer architecture or the Mistral architecture. As you can see, you have 32 attention heads, and each of these attention heads, for each of these attention heads, you are generating a query, a key, and a value to actually calculate, compute the attention result. This is also inside the transform architecture, just they didn't put the letters, but you can see the 3 arrows here and the 3 arrows here. And in general, in the initial architecture, you had for each query, you were calculating a key and a value, meaning that you had 32 queries, 32 keys, 32 values. Again, this is a lot of calculation, and after careful testing, researchers came out in the paper to the fact that some key and values could actually be shared and doesn't necessarily need to be recalculated. The trade-off is very minimal. This is why for 32 queries, so 42 attention heads, 32 queries, you are only computing 8 keys and 8 values. So it's a division by 4. It's 4 times less than what was actually initially calculated in the initial transformer architecture. So this is again a very strategic choice. As you can see here, we are inside Mistral. The key and values are shared between the different queries for, in the end, very minimal trade-off. This again, as said, drastically reduced the computation needed, the memory footprint to store all of these internal and temporary calculation, and as a result, increase drastically the inference speed. Okay, we are done with the technical part. Now we can have finally a look at nice and colorful charts. Let's look at the benchmarks. Mistral is laying out from the beginning of the paper, is showing immediately and very proudly how well Mistral 7B is performing in comparison with other LLMs. So at that time, the direct concurrents were in the open source models. As open source models were the Llama models, so Llama 2 7B, Llama 2 13B, and Llama 1 34 billion, because I think at that time Llama 2 34 billion was not open sourced yet. So those are the 3 models used for the comparison. And I put you on the right the table that is given in the paper, and put some colors into it just to to show how well Mistral 7b stands out in terms of benchmark results. Mistral AI ran benchmark into 6 different categories. Popular aggregated result, common sense reasoning, reading comprehension, word knowledge, code, and math, especially to show that that's very different benchmark addressing very different type of use case, and they want to show how well Mistral 7b shines at generalizing at a wide range of tasks. The results speak for themselves. Mistral 7b outperformed large language model on almost all of the benchmark, especially key one like the MMLU. It shows reasoning superiority, especially for human-aligned application. Mistral 7b is great at reasoning. We see it here in the math. You can see like its domination in the math, solving math problem, even in the code category, and in the reasoning one, that it is approaching it is matching the performance of the 34 billion models of Llama 1. What's even more surprising is that it is excellent at writing code. So if the table compare it to Code Llama 7b, which is a Llama model that has been fine-tuned to produce code. So it is a model that has been made especially for generating code, and still Mistral 7b comes very close to on the two coding benchmark, very close to the result of Code Llama 7b, without doing any compromises on the other benchmarks. So it is impressive how good it is at producing code. What are the trade-offs? There is actually only one main trade-off because of the small size of Mistral. Mistral 7b, as its name indicates, has 7 billion parameters, which is very small. And because of its small size, there is so much knowledge that it can actually remember, that it can actually hold into its weight. And this is where actually you have a small trade-off in the knowledge benchmark. Because of its small size, Mistral 7b is matching. Mistral 7b cannot outperforms bigger models like the 34 billion parameter of Llama 1, which has way more parameters, which more weights to actually hold real-world application, real-world knowledge. However, if you check the graph, it is still matching Llama 2 13 billion, so it can retain in almost half of the weight as much information as the 13 billion parameter model. Actually, I didn't put it in the presentation, but they give a very interesting, very interesting comparison. They estimate the equivalent Llama model. They compare actually Mistral and Llama, and they say, for example, that on the MMLU benchmark, Mistral is equivalent to a Llama 2 model of size 23 billion. In reasoning, you can see it's equivalent to a 38 billion. In knowledge, as we said, this is where the trade-off is affecting. It's about it's matching the Llama 2 13 billion, and in comprehension, Mistral approximates, in theory, a Llama model of size 21 billion. So you can see the size equivalencies are pretty impressive. Mistral 7b is a state-of-the-art, very efficient, very performance LLM into a very compact design. Yeah, I put it here. Llama 2, equivalent to a Llama 2 model of size 13 billion in word knowledge or 38 billion in reasoning. This is very impressive, and it is directly addressing the concern that you don't necessarily need big model to get great performance. The compression ratio, the way that information are compressed inside Mistral, shows actually that a great compression, that information can be compressed in a way that the model still retains all of its efficiency at inference time. Okay, let's move to fine-tuning. As I said earlier, as I said at the beginning, it's not, Mistral 7B is not just a research project. It's not just some LLM that 3 guys has developed in their garage and spit to the world saying, hey, look, we have good result, it's good. No, Mistral straight from the beginning has been made to be used on real world scenarios. And this is why in the paper you have a full section on fine-tuning, because Mistral wants to show that their model can generalize pretty well and address a real-world use case. So they provide, next to the native version of Mistral, they provide a fine-tuned version called Mistral 7B Instruct. And this version has been fine-tuned, so has been trained on public datasets. So we don't really know what dataset, but they say in the paper they use Hugging Face public datasets to train it, and then they have tested it on real-world use case on different types of benchmark. Here you have the result on 2 benchmark. The chatbot area Elo rating, which is a benchmark that evaluate, you have real human evaluating the quality of the model being used as a chatbot. So they evaluate, they compare the answer of 2 models, probably I think Mistral and Llama 2, and they compare the answer from the LLM, and they grade how well the chatbot answers are. And the empty bench, which is tour by tour conversation benchmark, evaluating how well the LLM is able to follow conversation and stick to the conversation using this tour by tour discussion like human beings. Again, it strikes out that Mistral 7B is widely over the Llama model, even the 13 billion ones, and is really at the top, is really shining at the top of the podium. That makes of Mistral 7B a very versatile model aimed at being used immediately on real-world applications. One thing we haven't discussed are the guardrails. So guardrails are safety measures implemented in front-facing application to implemented into the LLM to especially to address front-facing applications, safety in front-facing applications. It's important to say that when Mistral came out, the native version of Mistral actually doesn't have any guardrails implemented. This actually, probably you have noticed when Mistral was released last year, it followed a lot of people on YouTube and LinkedIn showing actually that the model was uncensored and showing how to use Mistral as an uncensored model, and were actually really concerned by the fact that it can produce actually any kind of content, and it doesn't have the reassuring guardrails that we have, for example, if you use ChatGPT. When you talk to ChatGPT, if you start talking about dangerous substances, about anything that's not that doesn't fit to its guardrails, it will politely deny to speak about it and say it's not allowed to. But at the same time, again, in the optic that Mistral should be used in real-world application, Mistral AI dedicated a full section of the paper about guardrails and showing that they came up with a way to implement some efficient guardrails to make sure that the fine-tuned version of the model can follow explicit instruction responsively. For this, they use prompt fine-tuning, and they provide an example of prompt in the paper. That's the one in gray, that you can integrate into your prompt to make sure that the model is not gonna produce harmful, unethical, prejudice, negative content, etc. So this is the first step. By using prompt fine-tuning, you can implement those guardrails. And there is another mechanism called the self-reflection mechanism that they mention, which is a mechanism that allow Mistral to revisit its own output, meaning that when Mistral produces an output, when it generates an answer to the user query, it will go into a step of reviewing its own answer, reviewing its own generated answer, and making sure that it is not flagged again as prejudice, negative, unethical, harmful, etc. And the accuracy of this step is over 99%. Finally, it is still important to mention that Mistral 7b is open source, fully transparent, and engineers can audit and enhance the safety, can implement some audit and safety enhancement steps. Mistral loves benchmarks, so they, even for the guardrails, provide one showing that when using the guardrails and compared to a Llama 2 model using a similar system, similar guardrails in their system prompt, Mistral is still on the MT benchmark, so the 2x2 conversation benchmark is still scoring a pretty good score. And the performance of using the guardrails, it's not drastically impacting the model, so you can still implement those guardrails and retain the full performance of Mistral. Yeah, and they give an also, just to compare the two, a funny example when they ask Llama 2 and Mistral to how to kill a Linux process, and actually only Mistral is providing an answer, while Llama 2 actually deny and doesn't want to answer. Okay, we are coming slowly to the end. I want to finish with some use cases. I'm going to say it once again, Mistral has been made to be used in real-world use case. Mistral, by releasing their first model, wants to take a piece of the cake and has already set the bar very high and say, we have released the first model, it is made to be used for real-world scenario and to outperforms and compete, outperforms the Llama model and compete with the bigger ones, with the giants like OpenAI and Anthropic. It can be used for creative and technical problem-solving tasks, so it generalizes very well. It is not doing too much trade-off. It is very good in a wide range of scenario. It can be used as a chatbot, like we discussed, as a content moderator, can do multilingual translation, summarize documents, retrieve knowledge, in spite, even as we said, of its small size. Is very well at generating code, tackling math problem, can be used in education, etc. So it's a very versatile model. It is, because of its internal optimization and reduced calculation, it performs great in low resource environment in case of edge deployment. Obviously, you have no inference cost because you are running it locally. One thing that I find very interesting is that in the case of data privacy, because you are using a model internally, you can download it from Hugging Face and use it internally. You don't need to rely on any cloud or any calls to the outside. Like, for example, if you use OpenAI, if you use a GPT model, you have to rely on calls, meaning that you have to send some company information, company knowledge to the outside that will be saved somewhere in the cloud. And this could be, for many companies, a very drastic question, very drastic topic. By using a model like Mistral internally, you have a full control over your data and over sharing your data. And because Mistral is open source and transparent, you know exactly what's happening under the hood. And finally, thanks to the Apache 2.0 license, you have full control over what you do with it, what you want to share, and how you want to use it. Again, this places Mistral immediately as it's released as a direct concurrent of the other open source model. Okay, conclusion, what are the key takeaways and why is Mistral 7b so good? Let's say it one last time. It is small, it is powerful, and it outperforms the bigger models on the paper and approaches the the performance of the giants of GPT models and cloud models. It is highly efficient and scalable thanks to its optimized memory footprint, optimized internal calculation, and the different strategies we have discussed. It is lightweight, highly adaptable to low resource hardware, making it key choices in case if you are working on some embedding device or some hardware that of very low resources. It is, as we have seen, versatile across a wide range of use cases with very minimal trade-off in some of them. And finally, it is open source, fully transparent, and highly customizable. They finished at the paper, they addressed this main question: how can we make large language models smaller but still retain all of their performance? And this is a question that I think researchers have been working very, very intensely in the past 2-3 years. We are seeing the end of this paradigm that huge model, that only big model provide great performance. We are seeing smaller model getting even more performant, and we are now spending a lot of time trying to minimize the size of the model. Why? Because in the end, we all want an LLM working on our smartphones, in our car, in our microwave, maybe on our fridge. And because of the low resource hardware, and because of the cost also of training those those giant model, the amount of GPU power and computation that are required, we are moving towards LLM that will be in the future smaller, easier to implement, faster to infer on, but still while still retaining all of the performance. And I think lately I have seen some 1 billion parameter model pop up on LinkedIn showing impressive performance on the benchmark. And I think this is the right direction to go. Okay, I want to thank you for your attention. I hope this was useful for you too. I had a great time actually going through this paper. I encourage you to read it. It's actually pretty easy to read, apart maybe from the architecture and strategies and sliding windows and all of this. But you have a lot of blogs and information about it. If you want to dig more on Transformer, I can highly recommend this series of videos from 3 Blue 1 Brown, especially the one on the Transformer architecture. They have helped me immensely to understand how the attention mechanism is working, and then basically what Mistral has been doing to improve it. And obviously, I encourage you to download Mistral, fine-tune it, play with it. I've done that in my last bootcamp, and I had a blast doing that. It's a very great model to work with. Thank you very much, and stay tuned for more interesting stuff. Bye-bye.